Hello and welcome. Today we're going to explore a common challenge in Python programming, managing asynchronous tasks. We'll look at a powerful tool called Celery that helps solve this problem. Celery is an open source library that makes it easy to handle asynchronous and parallel tasks in Python applications. While Celery's core engine can actually work with different programming languages, we'll focus specifically on using it with Python. To get started, you'll need an IDE or integrated development environment of your choice. Although we'll spend a lot of time writing code in the IDE, we also need to think about the infrastructure that supports our application. This includes two important components, a broker and a backend. To keep things simple, we'll use Redis to serve as both our broker and backend in this demonstration. While you could run everything we'll show you on your personal computer, we want to give you a more professional, production-ready example. We'll do this by using Google Kubernetes Engine, which will show you how to deploy these tools in a real-world environment using Docker containers. Don't worry if you're using a different system though, you should still be able to follow along and learn the concepts. Let's begin by creating two important files. First, we'll make a file called usageexamples.py for our demonstration. We'll also create a second file called app.py that will contain our task definitions. In app.py, we'll show you several examples of what Celery can do. Remember that Celery is fundamentally a task processing system. This means we need to first set up Celery with our broker and backend, and then we can use this setup to run tasks asynchronously and in parallel. In our code, we use something called a decorator, written as @app.task, to mark our functions as Celery tasks. These tasks can be very simple, like adding two numbers together, or they can be much more complex and time-consuming. For example, we can create a task that simulates long-running operations using a sleep function, or we can make tasks that call external APIs and process the results. One powerful feature of Celery is its ability to chain tasks together. This means we can take the output from one task and use it as input for another task. Celery also offers some advanced features like routing tasks based on their priority and sophisticated error handling. For instance, if a task fails, Celery can automatically try to run it again a certain number of times. You can even set up periodic tasks that run automatically at regular intervals, such as every 30 minutes. Now let's set up our development environment, starting with our local system before moving to Google Kubernetes Engine. First, we need to create and activate a virtual environment. Then we'll install the necessary packages using pip. We'll need two main libraries, Celery with Redis support and the requests library. We also need to install a local Redis server. Once Redis is installed, we can start it by simply running the Redis server command. With Redis running and ready to accept connections, we'll need to keep that process running in a separate terminal window. Now we can start working with Celery. We'll begin by starting a Celery worker, using our app.py file and enabling verbose logging so we can see exactly what's happening. Let's run our example tasks and watch what happens. In the worker terminal, you can see the tasks being received and processed. One interesting thing to notice is our weather task. It's automatically retrying because it's trying to get data from an API without having an API key. Meanwhile, other tasks are completing successfully. For example, our simple addition task has finished, and our long-running tasks have completed after their expected 5-second duration. An important point to understand is that we're currently only using a single worker, but Celery's real power comes from its ability to use multiple workers. We can demonstrate this by opening another terminal tab and starting a second worker using the exact same command. This gives us 2 workers with very little effort. Since our first worker is busy processing tasks, having this second worker will help handle the workload. When we run our usage examples again, you'll see tasks being distributed between both workers. They actively compete to process tasks as they become available. We still have that weather task repeatedly retrying without success. After examining these failures, let's move forward without it for now. While we have a small issue with our progress tracking example, you can still observe how the progress tracking works. We can also see our task chaining in action, where multiple tasks run in sequence, and our parallel tasks example. All of these tasks can run on either of our workers, giving us flexible task processing capabilities. Now let's move on to deploying our application in a more professional, production-ready way. We'll need a few key files for this. First, we need a requirements.txt file that lists our dependencies, specifically the requests and Celery libraries. We also need a Docker file that will package up our usage examples and prepare them to run. For our Kubernetes setup, we'll need several resources. This includes configurations for our workers, the main application itself, and the services and deployments for Redis. Let's set this up step by step. Our first task is creating a place to store our Docker image. We'll do this by enabling Google's Artifact Registry service and creating a Docker registry for our application. Once we have the registry path, we can build and push our Docker image using the console. While our image is being pushed, we can create our Kubernetes cluster. We'll do this through the clusters page, and for simplicity, we can use all the default settings that come with autopilot mode. After our cluster is ready, we can deploy our resources. We just need to make sure we're using the correct image path that we pushed earlier in our Kubernetes configurations. Something important to note is that we're using the same Docker image for both the Celery application and the Celery worker. The only difference is the command that runs when the container starts, since both components need the same code and overall setup. We'll also set up a scheduler that will periodically start tasks at regular intervals, which will then be executed by our 2 workers. With our cluster ready, we can deploy everything and watch its status. We have several components to monitor: our 2 workers, our job scheduler, and the system that handles periodic tasks. At this point, we can shut down our local testing environment since our 2 workers and Redis service are now running fully in the cloud. We've successfully moved to a production environment. As things come online, we should check the logs to make sure everything is working correctly. We can see that our Redis instance has started up. While our workers aren't showing any activity yet, our job is running. However, we notice we need to update some of our references. The Redis service is set up correctly for our job, and we're inheriting most settings from our config map, which should work well. To be more explicit about our configuration, we need to update our app.py file to use environment variables. We'll set up the broker URL to reference our tasks service. This updated configuration should prevent communication issues that happen when we try to use localhost in a distributed environment. Let's rebuild and push our updated application, then remove our existing resources and recreate them with a new configuration. we notice one error we introduced. We need to add an import statement for the OS module. After updating these resources, we start seeing activity in our logs. Our first worker is receiving new tasks, including process number tasks and format result tasks. All of this activity shows that our job has completed successfully and everything is running as expected. We notice an interesting pattern. Since the first worker came online quickly, it processed all the requests before the second worker could start handling tasks. While this isn't ideal for load balancing, it still demonstrates that our simple example is working in a distributed production-grade environment. One final important note: when you're working in a production environment, you'll probably want to use an infrastructure as code tool like Terraform to set up your Kubernetes cluster and possibly even your Kubernetes resources. The actual infrastructure needed is quite minimal, mainly just a container service like Elastic Kubernetes Engine or Google Kubernetes Engine, plus some networking components. This setup demonstrates how you can take a simple Celery application from local development to a production-ready deployment. While we used Google Kubernetes Engine, the same principles apply to other cloud platforms or your own infrastructure. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code and the diagram file in the description as well. If you have any questions, please post them in the comment section, and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.